All right, so in this one, we are going to look at dividing radicals. So in our last lesson, we looked at multiplying radicals, where as long as we have radicals with the same index, so type of root, we are allowed to multiply them together. And you can just multiply the whole numbers together and then multiply the radicals together and put them under the same root. So the process is quite the same with dividing radicals. So once again, we would look and see, do we have whole numbers in front, so part of the mixed radical? Can we divide those? What's the answer? And then as long as the index is the same, we can then divide the radicands as well. So in this case, we have 4 cube root of 6 divided by 2 cube root of 3. So I'll start by dividing my whole numbers. So what I'm going to do there is say, okay, well, 4 divided by 2, look at that and say, okay, well, 4 divided by 2, that's just 2. And then I'm going to look at my radical parts. Well, they're both cube roots, so I can in fact divide those, okay? And I'll just put them under the same radicand, okay? So that is just going to mean now that I can have the cube root of 6 divided by the cube root of 3. So that's going to now become the cube root of 6 divided by 3. So that's 2 times the cube root of, and 6 divided by 3 is, of course, 2. And I can't simplify that any further, so that would be my final answer here. Okay, so divide your whole numbers, divide your radicands, providing you have the same index. Okay? And the same thing again works with variables, right? So here I have the square root of 24x squared divided by the square root of 3x, and they've given me a restriction where x needs to be bigger than 0, which makes sense because it's a square root and square roots need to be positive. So what I'm dealing with here is this square root of 24x squared divided by the square root of 3x. Because the index is the same, they're both square roots, I can put that under a single square root. So I can rewrite that as the square root of 24x squared over 3x. Okay, so it can all go under one big square root. Now I can do division of my numbers, division of my variables. So 24 divided by 3 is 8. So this is again all still under the square root. 24 divided by 3 is 8. X squared divided by x is just a single x. Right, so you're essentially using exponent laws there, where when you're dividing powers with the same base, you subtract the exponents. So this is x squared, and this is x to the power of 1. So 2 minus 1 is just 1. So what we have at this point is the square root of 8x. Now, like we do with everything, we're going to ask ourselves, can we simplify this? Does 8 or x have any perfect square factors? And 8 absolutely does. It can be broken down into root 4 times root 2, and then of course we still have this root x. The square root of 4 is in fact 2. Can't do anything with the root 2 or the root x, so it's 2 times root 2x, and this is my final answer here. Okay? So when you're dividing, just make sure that you have the same index. You can just straight division with the radicands between each other and simplify as you go. Okay? Where things can become a little bit more interesting is in a process called rationalizing the denominator. So it's proper math form to not have irrational numbers like radicals in our denominator. So we like to see our denominators only as whole numbers. So if you end up with an expression where there is a radical in the denominator, you need to get rid of it, called rationalizing, right? So you're rationalizing your denominator. So oftentimes what we need to do here is, because it's just an expression, not an equation, we need to multiply by clever forms of 1. And you're picking this clever form of 1 in a way so that it will in fact remove the radical. So you have to think to yourself, what can I multiply this radical by so that it will cancel itself out? And if you think about it, if it's a square root, if you multiply a square root by a square root, it just equals the same thing. So here in this example, what we have is 14 divided by the square root of 2. Now if I take the square root of 2 and multiply it by the square root of 2, it's the square root of 4, which is 2. So that's going to be what I'm going to choose as my clever form of 1. I'm going to multiply it by root 2 over root 2. Right? And that's going to equal, now just we're multiplying fractions here, so we multiply the fraction, numerator by the numerator, so 14 times root 2 is just 14 root 2, and we're multiplying the denominator, so root 2 times root 2 is root 4, which like we just said is 2. Then we can divide. So again, we can see that we have whole numbers that can be divided. 14 divided by 2 is in fact 7. And then root 2 divided by 1 is just going to be root 2. Okay? So we just need to kind of choose this clever form of 1 to get rid of that denominator. So again, what we have here is 4 root 5n divided by 3 times root 2. Again, we've been given that restriction that n must be positive because it's a square root and square roots have to be positive. So all we're doing here is we are just trying to rationalize that denominator. What can I multiply by that gets rid of that root 2? And again, it's just the root 2. So what we would have is this 4 root 5n over 3 root 2 okay, so over 3 root 2, and we're multiplying by a clever form of 1, right? So we want to get rid of that root 2, so if we multiply both top and bottom by root 2, we can just multiply fractions here. So 4 root 5n times root 2, so again, whole numbers being multiplied together, so it's like 4 times essentially 1 here, which is 4, and then root 5n times root 2 is root 10n. And then in the denominator, same type of thing, it's 3 times essentially 1. Okay. So it's essentially 3 times 1 here, so that's 3, and then root 2 times root 2 is root 4. And I'll show this step for this case. So what we have here is 4 root 10n divided by 3 times root 4, which is 2. You can see now that the radical is gone, and what we have is 4 root 10n divided by 6. And now we're at the stage of simplifying. So we've done the job of rationalizing it. The denominator does not have a radical. Now it's just a matter of looking at, well, is there any common factors between the numerator and the denominator, or can that radical be simplified? So just looking at the radical of the square root of 10n, 10 does not have any perfect square factors. It is not divisible by 4 or 9. And n obviously doesn't have a high enough exponent to work, so that's fine as it is. But what you should notice here is that both the 4 and the 6 have a common factor of 2, which essentially means you're factoring out a 2, and you're rewriting this as 2 times 2 root 10n, and you're rewriting the denominator as 2 times 3, and then you're just canceling the 2's, and your most simplified expression is 2 root 10n over 3, right? So similar to what we were doing with rational expressions as well, finding common factors and canceling them out. And that would be our final answer there, okay? Some people will ask, well, instead of multiplying by root 2 over root 2, could I have multiplied by 3 root 2? And the answer is yes, and just so you can kind of see what that would look like, it just means that you're going to have a lot more simplifying that you're going to have to do, right? Because if you multiplied that by 3 root 2 over 3 root 2, when you do this multiplication, you'll get 12 times root 10n. And then here, you would get 3 times 3, so whole numbers multiplied is 9. And then root 2 times root 2 is 2. So then what you have is this 12 root 10n over 18. And it just means that that needed to be simplified more. But you do get the same thing, and it's just the common factor now is 6. And it's 6 times 2 root 10n over 6 times 3, and again the 6's cancel, and you get the exact same answer. Okay, so you can do it by the entire denominator in that case, but the simplest way to do it is just to pick the radical, because that's the thing that you're trying to get rid of. All right, where things can become even a little bit more complicated is what happens when there's a radical in the denominator, but it's not just a single term. There's 2 terms, and we need to get rid of both of them. Okay. In that case, you're still multiplying by that clever form of 1, but the clever form of 1 is not just whatever that radical is, it's what we call the conjugate, which is where you use both of the exact same terms, you just switch the sign. So in this example here, what we have is 7 root 2 divided by 4 minus root 3. Okay, so there's clearly 2 terms, right? They're separated by a subtraction sign. There's 2 terms here. And I'm just going to kind of show you why multiplying by just root 3 over root 3 isn't going to work. So let's suppose we did try that, and we multiplied by root 3 over root 3. What we would get is 7 root 6 over, and then this would have to be the distributive property here where you'd have to do 4 times root 3, which is 4 root 3, minus root 3 times root 3, which is minus root 9, so minus 3. Notice how this didn't actually get rid of our radical in the denominator. It just put it in a different spot. Okay? So doing this is not really helpful because it will remove the radical from one of the terms, but it will add it to one of the other terms. So this is, like I said, this is why we need this concept of a conjugate. So, like I said, the conjugate is found by just taking the exact same terms, but switching the sign. So it's going to be 4 plus root 3 over 4 plus root 3. And again, it's an expression, so I can't just add to it or subtract to it. The only thing I can do is multiply by 1. So this is my clever form of 1. And at this point, we're again just multiplying fractions. Right, so numerator times numerator, so that's 7 root 2 times 4. So multiply your whole numbers together. That'll be 28 root 2. And then 7 root 2 times root 3, which will be 7 root 6. And then in my denominator down here, it's going to go 4 times 4, which is 16. 4 times positive root 3, which is 4 root 3. Then negative root 3 times 4, which is negative 4 root 3. And negative root 3 times positive root 3, which is negative root 9. You're thinking, okay, well, there's still radicals there, but watch what happens. So our numerator is fine as it is, 28 root 2 plus 7 root 6. We're okay with radicals in the numerator, we just don't want them in the denominator. But positive 4 root 3 and negative 4 root 3, they're going to cancel. And root 9 is actually just 3. So what we're left with here is just 16 minus 3. So our final answer here is 28 root 2 plus 7 root 6 all over 13. And we have rationalized our denominator. The denominator does not contain any radicals. Okay? So we'll take a look at another example here. So we have 5 root 3 over 4 minus root 6. So again, because there are 2 terms in the denominator, right, they're separated by a minus sign, I need to multiply by a clever form of 1 that needs to be a conjugate. And again, that conjugate is using the same terms but separating them by a different sign. So my clever form of 1 here is going to be 4 plus root 6 over 4 plus root 6. Right? And then once again, I am just multiplying fractions, multiply the numerators, multiply the denominators. So here it's 5 root 3 times 4, so that will give me 20 root 3. Then it's 5 root 3 times root 6, which is 5 root 18. Okay, and then in the denominator, we're going to do that same thing. So 4 times 4 is 16. 4 times positive root 6 is a plus 4 root 6. And then negative 6 root 6 times 4 is negative 4 root 6. And then negative root 6 times positive root 6 will be negative root 36. And again, we have 20 root 3 plus 5 root 18 divided by 16. The plus 4 root 6 and the negative 4 root 6 cancel, and then root 36 is just 6, so it's minus 10, 16 minus 6, which is 10. So what we have is 20 root 3 plus 5 root 18 over 10. But one last check, we need to make sure that everything is as simplified as possible, so we look at term by term. So 20 root 3, nothing I can do there. But 5 root 18, 18 does have a perfect square factor. It's divisible by 9. So we can now take a look at that and say, all right, well, we'll leave the 20 root 3 as it is. And we can rewrite 5 root 18 as 5 root 9 times root 2. That's all over 10. Carrying on, we have 20 root 3 plus root 9 is 3, and 3 times 5 is 15, root 2 over 10. Can't combine those 2 terms in the numerator because the radicands are different, so I have one that's root 3, one that's root 2. However, I can now start looking at, is there a common factor between things in the numerator and in the denominator? And it should be fairly obvious that every single one of those terms is divisible by 5. So I can factor out a 5 from this numerator and it becomes 5 times 4 root 3 plus 3 root 2 all over 5 times 2. The 5's cancel, and my final answer is 4 root 3 plus 3 root 2 all over 2. All right, so rationalize the denominator, check. Simplified as much as I can, check. Okay, so let's just look at one final example here. So again, 11 over root 5 plus 7. So we're looking to rationalize the denominator. So because there are two terms, root 5 and a plus 7, I'm going to need a conjugate as my clever form of 1, which means it's going to be root 5 minus 7. So it's the same terms, you just switch the sign that's in between them. And then we're multiplying. Okay, so that's 11 times root 5, which is 11 root 5. 11 times negative 7, which is negative 77, divided by, okay, then root 5 times root 5, which is root 25, okay, which we just did, and then root 5 times negative 7, which is negative 7 root 5, and then positive 7 times root 5 is a plus 7 root 5, and then positive 7 times negative 7, which is negative 49. Simplify where we can, so 11 root 5 minus 77 divided by root 25 is just 5. Negative 7 root 5 cancels with the positive 7 root 5, and then minus 49 here. Okay, so simplify the denominator, leave the numerator the same, 11 root 5 minus 77, all over 5 minus 44, or 5 minus 49, which is negative 44. And our final step to check for is, can anything be simplified? So the radical is a root 5, that's prime, so it has no perfect square factors. And then we can look at all the other terms and say, is there something in common between the terms in the numerator and the denominator? And it should be fairly obvious that it's an 11. So we can factor an 11 from both the numerator and the denominator. So this is 11 times root 5 minus 7, all over 11 times negative 4. The 11's can cancel, and what I'm left with is root 5 minus 7 all over negative 4. I've rationalized the denominator, there is no radical in there, and I have simplified as best as I can. Okay, so that's simplifying through division of radicals, right, and being able to rationalize the denominator by, either multiplying by clever forms of 1 of just the radical or a conjugate if necessary. All right, and then these are the questions I'd like you to attempt using the information from this lesson.